Hello there. In this lesson we're going to see mechanisms as a locus of a point. We're going to see various examples of cranks and pistons and sliders. We're going to give in information on what the system does and then asked for the locus of a certain point. In this case we need to find the locus of point P. So what we have here is a crank OA. It's an arm that rotates about O. So the locus of B would be a circle. To it I've got a connecting rod connected to this slider here, or a piston, where it can only slide along this horizontal axis. So for one revolution of OB I need to find the locus of P. Now if you're asked for a revolution of OB, that's where I need to start off from. That's the locus of point B. It's a circle, because O is a fixed center. Now BA and OB, their distances will always remain unchanged. Their angles will change, but their lengths will always be the same. So the method of finding the locus of point P is to take, for one revolution, take a number of snapshots of the system and then mark point P on each point. So this distance BA, B is always going to be on the circle and A is always going to be on the line. Now if you take randomly a number of points along the circle and always mark from the circle to the line, you'll get a good number of points. But to do it more systematically and get an even distribution of points, I'm going to take 12 divisions of the circle. I'm going to divide the circle into 12 parts so that I get 12 points equally distributed along the circumference, along the locus of B. This is an easy way how to divide a circle into 12 parts, taking the radius of the same circle. It doesn't really matter if it's going clockwise or anti-clockwise. I'm just going to number them, so then I know how to connect the dots. So take the distance from BA. 1 is here. I'm going to connect it and then mark off P on the new line. So that's the first point of point P. Same distance now from point 2 on the horizontal line. Taking point 2 to that line, and again taking point P on my number 2. That's number 2. I'm working a bit darker than I should so you can see the lines. That's point 3, and you keep going like this for the all 12 points. Again, the distance from B to P, taking from number 3 to my new line, and that's number 3. My locus so far is this curve. It would be a good idea to have two compasses. With one you can measure and leave it open the length of AB, and the other the length of BP. So here you've got your 4th point and your 5th, and point P from number 4 is here, and from number 5 is here. That's my locus so far. Now since this line, the slider is in line with the center, this is going to be a symmetrical locus. So each point I'm taking from the bottom part of the circle, should have left that like that, is going to coincide with the previous points I took to get a symmetrical locus. Try not to connect or mark off the points all at once, or else you get confused with all the lines that you've been drawn. You wouldn't know which one is which. Connecting point P, it's number 9, number 8, number 7, number 6. Number 10 is on the horizontal, and the last point is there, and I've completed the revolution of that locus. So it's a simple crank and slider, a crank and piston. We look at a different setup. Here I'm going to use a swivel or rotating bearing, which is C. I've got the same crank OB, which is going to revolve about O. So OB, which is providing the movement from whatever, from an engine or from a motor, is going to, the locus of B is that circle there. Now instead of having a slider, I've got a swivel bearing. Now swivel bearing is fixed, it won't move, unlike the slider we treated in the previous example. But what it does, BP slides through it and it's free to rotate. So when B, so this is a fixed point, when B goes down, the other end goes up. It's sliding through it. Notice that this point, point B, is always on the circle. So that's what the mechanism is doing. It's rotating on one end and doing the opposite on the other end. So what I need to do is every point, again, I'm going to take 12 divisions on the circle, so I could take 12 snapshots of the mechanism. These angles, again, they're not important at what angle they are or what angle they start, although they usually are given, because you need to draw all of them. So from which word you start is not really an issue. Now what you need to do here is, instead of marking first, I'm going to draw a line first. So this is the first point. The second point is going to go through the swivel bearing, but in that direction now. And this is the length of BP. That's the new position of P. Again, it goes through the swivel and keeps the same length. It goes through the swivel from the new point and keeps the same length. So that's the second position, that's the third position. New position of B, there, and that's my number 4. Notice that this distance is always changing, and so is this distance. But the whole distance of BP is always the same. New position from here through the swivel and marking my point 5. From here through the swivel, marking point 6. So far I've got this movement. That's the locus so far. All I have to do is continue this for 12 points. Through the swivel, mark off the length from B to P, number 7. Through the swivel, mark off the new distance, number 8, 7, 8. Nine, 10, and obviously if it's one revolution, you're going to finish off where you started off from. So it's always wise to join the dots all at once in the end to get a more smooth curve. Now with that swivel bearing rushed closer to the crank, you get a bigger locus here, because the switch would be greater. So that's the difference between the slider we did before and the swivel bearing or rotating bearing which we did now. Let's see another example. Here's what we call a glissette. A glissette would be no rotations in it, just straight lines. And we've got two pistons or sliders. A is going to move on this horizontal line. B can only move on this vertical line. So what happens is I've got a vertical bar like that, where A can move from here to here, and B, which is fixed on the point, can move upwards. Alright, so when A moves this way, B must, to keep the same distance, move upwards until you get to the vertical position, to the horizontal position. Now in this question I want the locus of the point P. So this example, a practical example, would be how a garage door opens. Those up and over garage doors. In that position it goes up like that. So the distance here, which always remains the same, is AB and BP. A is going to move from this position to this position. How far away would A move? It can only move the same distance as A to B, because when B reaches here, it can move no more, so that the distance AB here is the same distance here. Now, how many divisions I'm going to take? Now that depends on the question how large you're drawing. I usually take 6 divisions on such a line. There's no really need to take them equidistant, but we do just to keep it a bit neater. So I'm going to take those different positions. That's the first position, second, third, fourth, fifth, and last position. So when A moves this distance to position 2, what happens to B? So I'm going to take the distance from AB, because these are the 2 points that are determining my movement. They're fixed. A goes here, B goes slightly upwards. Many make a mistake that if this is this division here, A moves this division here, they take up B the same division, same distance. Well, that will reduce the distance from A to B. What you want is always keeping that distance. So when A goes here, B goes there. And where would P be? P is the end of the rod. P would have to go upwards slightly. So what I'm going to do is I'm going to draw from my second division to the division I've marked, which is very close to the first division, and extend it a bit. How much should I extend it? You should extend it the same distance it was before. So BP is that distance, new BP is the same distance. So again, the distance from AB, taking from point 3 on the vertical line. Join the line and extend it. Extend it the same distance of BP. From 4 to there. drawing a line, and that's the distance BP. From 5 to the vertical. So that's what the new position of A, the new position of B. Connecting, extending, and marking. In the last position, when 6 is here, P would be out there. Now, since if you see you've got a too far gap from here to here, you can add another division between 5 and 6, so that you'll get another point somewhere between that distance. You can add as many divisions as you like. The more you take, the more points you have to join. The locus would be from P going upwards. That's the locus of the end of that glisset. Let's look at the final example I've got. Right here is that I've got a rotating arm, the crank AB, causing the movement, and then I've got an arm CD which is oscillating. It's going to and fro. Simulate this for a while. So B always moves along the circle. Now what C does, it holds it in place and then goes back again. It's going to hold it the same distance and then going back again. So what I need to do is, as I've already done here, I've drawn a circle around A, and the locus of C, since D is fixed, usually the symbol for fixed is something like that. I want distances. I don't want angles, I want distances. So AB is always that distance. It causes that locus for B. DC is always that distance. Now since D is fixed, C can only move in this arc. Now what happens is, when I've taken the 12 divisions as usual of the circle, I'm just going to do them randomly for now. Every time B moves a division, C must move the same distance. So BC is always the same distance. So when B moves here, C must be somewhere on that arc. Now DC, which is that distance away, should always be the same distance. C should always be the same distance from D and the same distance from B. So what you need to do is, from each point on the circle, I'm going to mark BC, and from each of those marks I have to intersect it with the same distance of CD. That's my new point. Now since DC is always the fixed point, it's much better off drawing that arc and then connecting each point from here to that arc. My first two positions I've done. So from here to my new position, it goes through that first intersecting point I did, and since CP is extended beyond C, here I've got my new P. So that was the first division, that's the second division. For number 3, from the first point I started marking off to my second intersecting arcs, going up the same distance away, and that's my new P, number 3. Again, I'm taking the distance BC from my fourth position to the arc, connecting point to the arc and extending it the same distance away. That's my point 4. BC from here to the arc. It's going back now. Join. Distance CP is extended beyond. That's my number 5. BC. Zoom in. BC. From my new position to the arc. Connected. Extended. Okay, right on the edge of the paper. BC. Again, from here to here. Connect. One by one, don't try to draw everything all at once. And that's my new position, 7. BC. From the number 8. Connect. Extend. And mark off my new position, 8. You should get a loop since it's done a 1 revolution. So the original position from here to here. Join and extend, number 9. From here to here. Join and extend, number 10. From here to here. Join, since they're both the same distance away, and that's my number 10. I'm going to leave the last 2 points, just doing the same thing over and over again. And that would be your loop. Start off from point 1 to 3, going around, out of the paper, 7, 8, 9, 10. Oops, mistake, it's not number 10. 10 is over here, and cause that loop. Alright, so make sure that you're always marking the correct distances and you're connecting the correct lines. Now, since this is an oscillating arm, when I'm connecting from this point to this point, there are points that you could connect twice. So what do I mean by that? If you look at this arc, the arc can be extended as far as you like. Now when you're connecting from here to the arc, it can connect up here, it could connect down there as well. Each point can be marked off the circle twice. If you look at this point here, you can mark it here, and you can mark it there. Now always mark the nearest distance you were before in the previous point. And remember that since it's an oscillating arm, it's going back and then pushed, pulled and pushed to get that loop over there. Now there are thousands of different ways how to set up loci of mechanisms. I've included the most common types, but if you look at these, what could happen is that the sliders are in different angles, different positions. You could get, instead of a straight line here, you could have an elliptical track. You could have another swivel bearing at the end of this, so an arm would be connected through another swivel bearing, but the basis is the same. I can't possibly do it. It's useless doing a number of different examples because there are limitless setups of these cranks and mechanisms. Hope you found it helpful, especially for your exams, and especially Glenn Spiteri, because he's been asking for this for quite a while. Thank you.